we are going to see design of bell crank lever. This bell crank lever is having two arms which are at 90 degree to each other. The one arm is called as a load arm while the another arm is called as a effort arm, or it may be reverse, that this may be called as a load arm and this may be called as a effort arm, right? And where this both the arms get connected to each other, that particular point is called as a fulcrum point. And this fulcrum point, a fulcrum pin is inserted to this fulcrum point. While to reduce the wear of the fulcrum pin, there is a provision of bush. Similarly, the same type of arrangement is also provided over here at the two ends. At the two ends over here, there may be a pin, okay, at, I can say, at end B, and there is another pin over here which we can say end A. Okay, so same arrangement will be there. Obviously, again to reduce the excessive wear at point B and point A, a bush may be provided. So basically what we are having a lever which is having a two arms which are at 90 degree to each other. The center point, it is called as a fulcrum point, and pin is inserted into it. While the load arm is generally used, we are saying over here, this particular thing we are saying load arm, and this is effort arm. So this type of arrangement is there. Okay, so distance of the point A from the fulcrum is L1, while the distance of the point B from the fulcrum F is L2. Now the ends of this bell crank lever, that is at point A or at point B, at point A or at point B, these ends may look like this. It may be a fork end or it may be a single end. Okay, so this type of ends will be there which will be used to connect the another rods to this. So this type of arrangement is there. Now we will see how to design this. So first of all, what we will check, first of all, find the efforts needed. Find the efforts needed to raise the load W. Okay, so as we know, at one end load W is attached, so what effort is needed at the another end, that we are going to see. For that, what we have to do, we have to take the moment about the fulcrum O. So taking moment about fulcrum F. Okay, so what we can write down, W into its distance from the fulcrum point, that is L1, is equal to P into its distance from the fulcrum point, that is L2, that is W into L1 is equal to P into L2. So That is what we are going to do, and from this I can find out the effort needed. Effort is nothing but P is equal to W into L1 divided by L2. So what we get, what will be the effort needed to raise the load W. Now as we know, there will be a load at point A, there will be load W, and at point B there is a effort P. Now because of this there will be the reaction force, acting at point F, and we have to find out what will be this reaction force. So now I can say reaction force RF, we will say it RF, at the fulcrum pin at F. This will be equal to, by the law of parallelogram, as we know, law of parallelogram, if I draw over here, if this is W, if this is P, then by the law of parallelogram we know RF reaction force, if I consider this angle as a alpha, angle between these two, by the law of parallelogram we know that is RF is equal to, or RF is equal to under root W square plus P square plus 2 W into P cos alpha, right? But over here, alpha is 90 degree, and thus cos alpha is equal to cos 90, we will say cos 90 equals to 0, and that's why I can write down that is reaction force RF acting because of the load W and effort P is equal to under root W square plus P square. So from this what we are going to get? We are going to get what reaction forces are acting at the fulcrum point. Okay, that is the RF, and this will be equal to W square plus P square under root W square plus P square. Now we will design the fulcrum pin. Okay, so now this is the pin, and we are assuming the dimension of the pin, diameter of the pin is D and its length is L. So let diameter of pin at F, okay, at fulcrum point, I will write it down like this. Let D is diameter of pin at F and L is length of pin. Okay. Now, as we know, this particular bell crank may swivel or may move along this fulcrum pin, and because of this there will be a bearing pressure acting on this fulcrum pin. So what bearing pressure is going to act, that we are going to see. As we know, this particular fulcrum pin, and it is having it is rested in a bush like this, and because of this, whatever this portion is being there, this much portion, it will be exerted on the bearing pressure. Okay, so we know area on which bearing pressure is exerted, A1 is equal to what? This is nothing but diameter D, and this is the length L. So D into L, right? So we can say considering bearing pressure on the pin, how much pressure is how much force is being exerted on the pin? It is RF, right? Force is exerted is RF. So RF is equal to A1, that is cross sectional area, multiplied by PB. PB is, we can say, where PB is bearing pressure. What is the unit of pressure? Newton per meter square or Newton per millimeter square. So same as stress. So that is RF is equal to A1 into PB. So this is RF force acting. We know how much RF we just calculated. A1, that is A1 is nothing but D into L into PB. So we got this particular equation. So generally assuming length L of the pin is equal to 1.25 D. Assuming length of the pin is equal to 1.25 D. So this equation turns out to be RF is equal to D into 1.25 D into PB. So from this what we can get? Because here what is known to us, RF, what is known to us, RF is known, PB is known. So from this we can get the value of D. From this we can determine value of D and L, that is diameter of pin and length of pin. So we got the value of diameter of the pin and the length of the pin. So whatever the dimensions we got, now we have to check whether that dimensions are can sustain the load. Now when we are saying this pin, so when there will be the forces or RF, because of that what may happen, this pin may get shear out. So we have to check whatever the dimensions we calculated. Now we have to check the failure of the pin. So I can say, considering failure of pin in shear, or this will be actually a double shear, because we know this particular pin may shear out into three different parts. So it will be in the double shear, and this is the resisting area. So area resisting shear, or we can say resisting area, I will say it as A2 is equal to pi by 4 d square, because diameter of the pin is nothing but, we assume, we say it is a d, and that's why resisting area is pi by 4 d square. And as this, there is a double shear, that is two areas of pi by 4 d square is resisting this, and that's why 2 pi by 4 d square. And thus we can say we know shear force tau is equal to, how much force is acting on this pin, that is a reaction for RF divided by A2. So this turns out to be tau is equal to RF divided by 2 into pi by 4 d square. So from this we can get the value of induced stress. So from this equation, from this we get value of shear stress on the pin. Check this value with permissible shear stress. Okay, so if this value is lesser than the permissible shear stress value, then definitely your pin will be safe for the failure under shear. So that is what we check, that is whether the pin will sustain the shear forces. Okay, so this is what. Now we consider the failure of pin. Now what we are going to do, we will decide what will be the dimensions of the bush. As we know, this pin will be inserted into the bush. So in between the arms, or in between the lever and pin, there is a bush. So we have to fix the values of this bush. Actually, why we are using bush? So that there should not be the excessive wear of the pin and of the arm. So damage should not be transferred to the pin and damage should not be transferred to the lever, but whatever the wear will be there, that will be of the bush. So generally this bush material is softer material. Whatever the material we are using for pin or whatever the material we are using for the levers, the bush material will be softer, and this will be generally brass or something like that. Okay, so fixing the dimension of the bush. So bush is having a internal diameter db, and this internal diameter db will be equal to the diameter of the pin. Okay, because this pin will go inside to this bush, and this do, that is the outer diameter of the bush. Generally the thickness of the bush we considered as a 3 millimeter, and that's why I can say d0 is equal to d plus 2 into 3 millimeter. So this will be the value where db is internal diameter of the bush and do or do is outer diameter of the bush. So if the thickness of the bush is not given, then we will generally consider the thickness of the bush as a 3 millimeter, and that's why the outer diameter d0 can be found out. And obviously lb, that is length of the bush, will be equals to l, that is the length of the pin. So lb is length of bush, and this will be equal to length of pin. So in this way we fix the dimensions of the bush. Now whatever this bush is there, this bush will go in the hole which is present or which is drilled in the lever arm at the fulcrum point. So obviously we have to now fix the what should be the dimension of this hole in the lever arm at the fulcrum point. So what we are going to do, we are fixing the dimensions of the lever arm, hole at the lever arm at the fulcrum point at this particular point. So now in this, whatever the hole will be there, so in that there will be a bush will go. So the diameter of the hole should be equal to do, that is outer diameter of the bush. So let do diameter of the hole in the lever at fulcrum point. Okay, so this do, you know, do is equal to d plus 2 into 3, and what will be the outer diameter, and the outer diameter, that is that there will be a Bosch type arrangement and over here. So outer diameter at fulcrum point that is we are saying df is equal to 2d, that is twice d. So this is the empirical relation which we are going to use. So in this way we find out the diameter, outer diameter and inner diameter at the lever arm. Now we will check whatever this dimensions we fix. Now we will check the bending stress induced in the lever arm at the fulcrum point. Okay, so what will be the bending stresses at this particular point? What will be the bending stresses? So bending stresses, so we will take the bending moment at the fulcrum arm. So taking bending moment at fulcrum arm. Okay, so here this is the, if we take the cross section over here, we will get it like this, and this is LF D0 DF. So bending moment M is equal to, that is load W multiplied by distance, that is W into L1. Okay, and section modulus, now here whatever the section we are going to take over here, suppose I am saying this is a section XX, so this section is considered to be a rectangular section. Okay, and that's why section modulus Z is equal to, as we know, I divided by Y max, and this turns out to be for the rectangular section 1 by 12. Okay, we are taking along this 1 by 12 into LF multiplied by df cube minus d0 cube. Okay, so this, because at the center there is no material. Okay, and divided by df by 2, divided by df by 2, that is maximum distance, this distance, that is df by 2. So we know bending stress sigma b is equal to m by z, moment upon section modulus. So from this we can check how much bending stress is induced in the lever arm. Okay, from this we can check how much bending stress, is induced in the arm. Okay, and whether this is within the permissible limit or not. So once you check this, we will move to the next. That is, up till now what we have done, we have designed a pin at fulcrum point. Okay, so fulcrum point, at fulcrum point we design a pin at the fulcrum point F, and for that we also we also fix the dimension of bush, and then we also check the shear failure. Okay, so now there are other pins also. So we will now design the pin at point A. So if this is a point A, then here there will be another pin, and we will design the we will design the or finalize the dimensions of this point pin at A. So now again we will say let d1 is diameter of pin at point A, while L1 is length of pin at point A. So again we will consider the bearing pressure. Considering bearing pressure, because of load W. What load is being exerted on this point A? W, that is load W, and that's why I can say W is equal to area. I will say this is A3 multiplied by PB, that is bearing pressure, where A3 is equal to D1 into L1, and that's why we can write W is equal to D1 into L1 into PB, right? So we know the empirical relation between the length and D, assuming L1 is equal to 1.25 D1. So these equations turns out to be W is equal to D1 multiplied by 1.25 D1 into PB. So from this we can get the value of D1, that is diameter of the pin at A, and L1, that is length of the P at A. Okay, once you got this, we will check the failure of the pin in shear. Now considering failure of pin in double shear. So as we know, this pin, this will be torn out, this will be tear down into two parts, and the diameter is D1. So resisting area say A4 is equal to pi by 4 D1 square multiplied by 2, because it is in double shear, and that's why I can write down we know tau is equal to W. Now how much force is being exerted? W divided by A4. So this is equal to W divided by pi by 4 d1 square into 2. So from this we can check how much is the induced shear force and whether it is within the elastic limit, within the permissible limit or not. Okay. From this we can check the induced shear stress in the pin and whether it is within the elastic limit or not. If not, then we have to alter the dimension D and L. Okay. So that's what we have done. Now what we are going to do, we are going to check now whatever this shear stress, then obviously the same procedure we will follow, because there will be the bush. So fixing the dimension, dimensions of bush. So for the bush, the internal diameter I will say bush will look like this. Okay, so this is the dB and this is DO. dB internal diameter of bush, and this is equal to D1, that is diameter of the pin, and DO is outer diameter of bush, and we are considering the thickness is equal to 3 millimeter, and that's why DO is equal to D1 plus 2 into 3 millimeter. So this will be the outer diameter, and obviously LB is length of bush, and this is equal to L, that is length of pin. So here we finalize the bush also. Now we have to check, or we have to finalize the dimension of the hole at point A, or I can say fixing dimension of on lever at point A. So again Bosch type of arrangement will be there. It will have an internal hole and here bush will go, and that's why this dimension should be DO, and this will be, I say, DA, and it will be equals to twice D. So D0, as we know, this is equal to D1 plus 2 into 3 millimeter, and the outer diameter DA, if you remember the empirical relation, this is twice D1. So this we finalize. So dimensions are finalized for the hole at point A and the Bosch at point A. Now we will move and we will try, or we will check the bending moment at point A. So here at point A, the pin is neither supported nor rigidly fixed. At its end. Therefore, the common practice is to assume load distribution as shown. Okay, so load distribution, it is shown as this. So actually whatever this end is there, that end we are assuming to be a double fork end. Okay, so here there is a two fork end, and whatever the load is being there, that is total load W is acted, and here the load distribution is considered to be like this. So at L1 the load is distributed evenly, W by 2, W by 2, and at these two thickness ends, it is again UDL, uniform, it is distributed in this way. Okay, so maximum bending moment, if we consider the load distribution like this, then maximum bending moment will be at section YY. So whatever this section is there, Y, on this section maximum bending moment will appear. And this bending moment, how we can find out? We can take the left hand side or the right hand side of this section, and we can find out the bending moment. So M, how much load is acting on M? This is W by W by 2. And what is the distance from the section YY of the load W by 2? It is nothing but it is L1 by 2 plus T1 by 3, where T1 is nothing but thickness, of the double I fork end, and this is T1 by 3 minus, now if we consider this load, then minus W by 2 multiplied by L by 4 at a distance of L by 4 from the YY section YY. So this is a maximum bending moment, and if we solve this, then it comes to be 5 by 24 W into L1. Okay, considering T1 equals to L1 by 2. So what we are considering, thickness T1 is equal to L1 by 2. So this thickness, as it is a double I, so this thickness T1 is equal to L1 by 2. So this we are assuming, and from this actually we can find out the maximum bending moment. And now section modulus. Section modulus for the cross section, and this is how section modulus for the pin, and at the YY, and this is equal to, as pin is a circular, so pi by 32 D1 cube. Okay, so this is a section modulus, and we know bending stress or we can say the maximum bending stress is equal to moment divided by the section modulus, and from this what we can get the maximum bending moment induced, maximum bending stress induced. From this we get bending stress induced in a pin. Okay, so from this actually we have to check whether it is within the permissible limit or not, and then if it is within the permissible limit, then our design is safe. Now same procedure we are going to repeat at the design of pin at B. Okay, because there are two arms, and both the arms are having P at their extreme ends. So here again we are going to design, we are going to use the pin. So same procedure, may be adopted. Okay, so same procedure as previous one, that is at a design of the pin at A, may be adopted over here. Now design of lever. Actually now we have to finalize what is the cross section, what should be the cross section of the lever arm. So it is assumed that this lever extends up to the center of the fulcrum. Now whatever this lever is there, its cross section we are going to finalize. So it is assumed whatever this lever arm is there, that extends up to the center of the fulcrum, that is this lever arm extend up to the center of the fulcrum, up to this. Okay, from the point of application of load, wherever we are applying the load, from this lever arm extend up to this center. This assumption is commonly made and results in a slightly stronger section. So this assumption actually leads to the stronger section. Okay, and if we consider this cross sectional area and we are considering the rectangular section, the section or the cross sectional section of the lever may be rectangular, it may be I section, or it may be elliptical, but here we are considering it to be a rectangular section. Okay, so let B is the width of the section, width of the section at YY. We are considering the cross section at YY. Okay, that is not at the fulcrum point but somewhat away from this, and T is the thickness of the section, thickness of the lever arm. Thickness will be the constant throughout the length, width may change. Okay, so now if we assume, if we consider, if section YY is at a distance A from fulcrum point F, then taking moment about, then moment about section YY, what we will get, this will be equal to the load W into L1 minus A. Okay, so this moment we will get, and the section modulus Z is equal to 1 by 6 T into B square. Okay, so this is the section modulus, and this will be equal to 1 by 6 T into 3T square. Okay, so here assuming B is equal to thrice T. Okay, so if the relation between the width and the thickness is not given, we may assume the width is equal to thrice T. So from this again we know the bending stress sigma B is equal to bending moment M by Z, and from this we can get the value of B and T. From this we can determine B and T, that is width and thickness of the lever. Okay, so here we completed the design of the